Okay, this is for chemistry, Borger chemistry students. This is Unit 4 Atomic Structure and History, and this is PowerPoint number 2. Alright, find capital letter D on your notes. It should be on the first page. And capital letter D, again, we're talking about atomic structure. And you guys know a lot of this stuff already, or you should know a lot of this stuff already. You know that the atom is the smallest unit of an element that has the properties of that element. So when we say what's the smallest piece that you can get to, it's an atom. Now, we're very specific in that it's not an atom of sugar. Sugar's not on the periodic table. It's an atom of any of those 116 elements that are on the periodic table. So if you take any of those on the periodic table and you get the smallest piece of it that you can, that's an atom. And that atom, let's say of gold, again, has the properties that gold has. What color is it? It's gold. You know, it's just that it's a little bit difficult for us to pull up one atom of anything. So, you know, we generally talk about them in much greater amounts than just one atom. Okay, that atom can exist alone, or it can be in combination with others. So we can have pure gold. It can exist alone, an individual atom, or you can have a group of gold atoms. Or you can take that gold atom and chemically combine it to something else. So it can exist alone, or in combination with other atoms. Each of those atoms, every single atom that we talk about, is going to be made of 3 pieces: protons, neutrons, and electrons. And if you're asking me, oh, what about the quarks and leptons? We're not doing any of that. We're doing normal standard chemistry. We're not doing nuclear chemistry or nuclear physics at all. So we break the atom down into protons, neutrons, and electrons. All right, number 2 on your notes there. If you look capital letter D, number 2, and we're talking about the guy who really kind of started us off looking for different pieces within the atom. That is Henry Becquerel. I'm sure it's very nicely pronounced in French, but I don't pronounce it in French. So if you guys are in French class, great. You pronounce it the French way. As for me, it's Henry Becquerel. Now, Henry Becquerel discovered radiation, and because he discovered this radiation, he realized that, hey, that atom is actually divisible. It's not just this perfect, compact, small sphere. There are things within it. Now, you notice there's another video down there, so we're going to see some video clips talking about how they discovered different parts of the atoms. Now, when we talk about radiation, we're really talking about 3 major types. We have the alpha, beta, and gamma radiation is what we're talking about. Okay. All right, number 3. And since they decided that the atoms could be broken apart into pieces, they started looking for those pieces, and the first piece was discovered by J.J. Thomson, a lovely man. You see a picture of him there. And he used a cathode ray tube. And I've got something I'll show you. It's not exactly his setup, but I'll show you in class basically what he was looking at. But if you look at the picture here, he took something called a cathode ray tube, and it was this clear glass tube. And you suck all the air out of it, so it's a vacuum. And at each end, it had a metal piece. One end was the cathode, one end was the anode, a negative end and a positive end. Kind of like on batteries, they have a negative side and positive side. Kind of like that stuff. So he had this clear glass tube with negative and positive end that he was going to run electricity through. And then he put this little fluorescent screen inside of it. I don't know how he did it. It was just set up that way, okay? So he put this little fluorescent screen inside there, and he ran electricity through it, or cathode rays through it. And as the rays went down, it made the little screen light up. It fluoresced with a little line. And when he looked at it, it looks like just light. But when he put a magnet up to it, it caused the light to bend towards the magnet, wherever he put the magnet. And so he knew that it wasn't just light, because, you know, light doesn't work like that. You can get light from a candle and put a magnet to it, nothing happens. You can get light from a flashlight and put a magnet to it, nothing happens. But this stuff wasn't just light, because it was affected by that magnet. He said that electrons were what those little pieces were called. That little stream of electrons is what it's called. And in reality, electrons are really unique. As a matter of fact, our next unit will spend the whole unit talking about electrons, because they're kind of freaky. They have properties of both particles, like matter, solid matter, and waves, like energy, light. So they have an effect. They have a part to play in both matter and also light. So we'll talk about that in the next section that we do. All right, the pre-AP Chem students, you will be responsible for being able to explain what experiments were done, how they were done, and who did them. So just be aware. It'll be at the end of the set of notes here. Okay, number 3, electrons. So look on your notes. The electrons, again, were discovered by J.J. Thomson. You've already have that written down. Letter A, the electrons have properties of both particles and waves. I wrote that down too. And now we're on letter B, they're lightweight. They have almost no mass. And so when we talk about the mass of the atoms, the electrons, we just give them a mass of 0. We don't even count those. All electrons are negatively charged, and notice that the word negative is very boldly written there. You should know that. So it's lightweight and it's negatively charged. It's found somewhere outside the nucleus. Usually we have little pictures where it's orbiting the nucleus, and that's just a picture that we can use. It's a nice model to get inside of our head so we can kind of have an idea of what's going on. But it's somewhere outside the nucleus, and we'll talk about a better representation of how the electrons go around the nucleus in the next section. Its mass is really, really small. Letter D on your notes here if you're following along, which you should be because that's what you're doing. And then letter E, its negative charge is equal but opposite to the positive charge of the proton. So which is heavier, the proton or the electron? The proton is much heavier. However, when you're talking about charge, they're equal. The electron is negative and the proton is positive, but they have opposite charges and they're equal. So they balance each other out. If you have one electrons like -1, you have one protons like +1. When you add them together, +1, -1, you get 0. All right, all electrons look alike. You know, if you pull electrons from different types of elements, you can't tell which electron came from where. They all look alike. You can't tell them individually what they're like, what they come from. As a matter of fact, if you take a metal fork and stick it in an outlet, which would be a really stupid thing to do, by the way, just in case you were thinking about that. You have these little sparks coming out, so when you pick yourself up off the floor on the other side of the room, you'll have noticed that, oh yeah, there were these little sparks that came out. That's electricity. Moving electrons. That's what electricity is. All right, Thomson then came up with this ideal model of the atom, and he said it was kind of like plum pudding, which I have never eaten plum pudding before in my life. I don't know what it looks like, what it tastes like, or anything. So he calls it the plum pudding model. So let me give you an example that you might know of. Have you ever had that Jell-O that has little pieces of fruit in it? Okay, the Jell-O part would be the positive charges, and then, according to Thomson, and then the little fruit pieces inside would be the electrons, and they were just kind of spread throughout there. So that was his idea of what the atom looked like. Now, along came another guy, and there should be an arrow by his name too. Oh, yes, down at the bottom, letter G, 1913, Niels Bohr. And he looks like he almost looks sad. Whatever picture I see him, he almost has this hangdog expression, like, you know, life is bad. But Niels Bohr discovered that the electron orbits the nucleus. And he came up with the planetary model. And so you see all these little atom pictures around here? That's what most people associate when they see atoms. And he's the one who came up with this idea. It's not necessarily right, but it's a decent model, and it's easiest for us to picture in our heads. Now, Niels Bohr, if you look over to the west side of the room, there's a poster on the wall that says something about Bohr. Now, here are a couple of experiments that you're going to have to know. You're going to have to be able to discuss. And the first one, and this is all things that we're dealing with the parts of the atom here. There's a man by the name of Robert Millikan, one of the few Americans that was in the group here that was, you know, had all these brilliant physicists that were working on the parts of the atom, and Millikan was one of the Americans that was doing this. He's the guy that found the charge and the mass of the electron. The electron does have a mass, it's just really, really tiny. So what he did is he had this, and I don't know how these people come up with these experiments, but they're just amazing. He had these two metal plates, and he measured how far apart they were. They were parallel. And the top plate had a little bitty tiny hole in it. And then he hooked the metal plates up to a battery, and he could mess with the voltage. It was variable at will, so he could mess with how much electricity went through it. And then he looked at the space between the two metal plates with a microscope, so he was looking at really tiny pieces there. And then what he did is he sprayed a really light mist of oil above the plates. And then one little bitty tiny microscopic drop of oil fell through. And that's what he watched. When the plates were uncharged, he could actually measure how fast the drop went down, and he could get the speed. When the plates were charged when he ran electricity through them, he could mess with that drop. He could get it to go faster or slower. He could get it to actually go up. He could get it suspended there. He could do some really wicked stuff. And with all those measurements that he made, he was able to calculate the electrical charge that was on the drop, and he could calculate from that the electrical charge of an electron. And he found it to be 1.602 times 10 to the negative 19 coulombs. Then he used the charge to calculate the mass, and he did a ton of physics to get to this number. Are you expected to memorize all his calculations? No, and say, thank you, Lord, for that. If you didn't get all of this experiment, you can pause and go back and write down what you need to. Next one was J.J. Thomson's. We talked about his experiment, and what he did is he had that vacuum tube with an anode and a cathode. The positive end and the negative end, so one end was positive, one end was negative. And he placed a fluorescent screen inside, and he aimed the cathode ray beam right along it. And then he put a magnet near the tube, and the glow on the fluorescent screen bent, and I'll show you this in class. We don't have the exact same setup that he had, but we have some really cool stuff that you can really see what's going on here, how magnets affect this stuff. Now, when he put that magnet up to it, and it bent what looks like light, that proved that that glow wasn't just simply light, so he knew he could go on with that. And he was a good scientist because he went through and he did the exact same experiment, only he changed a variable each time. So he changed the metal that the anode and cathode were made of. He changed what type of gas was in there. He changed all different variables, and it was consistent all the way through. That little light that went through there was bent by that magnet. And so he said, hey, I'm thinking that the particles that make up this beam are little bitty pieces, and I'm going to call them electrons. And that's just I think it's Latin for beaming suns, which, okay, fine.